Okay, so today we will do cliques and independent sets. There is one difficult proof, something about the existence of triangles. But most of the statements I give will be observations from theory, where we won't be proving everything, basically. But these observations are very computational, very explicit formulas for when you will have certain cliques of size, certain size. And because they're so explicit, so applicable, sometimes we get these, say, easier questions in homeworks and exams involving clique sizes. Okay, so this section is less proof, less theory, but more formulas and more applicable results. So you may find this easier to follow. So this, I will remind you what a clique was, but we will have some formulas involving clique sizes and independent set sizes and so on. So first let me remind you what a complete graph is. A complete graph with n vertices is a graph with with vertex set V such that, of course, the size of V is n, and where for every V and W in V, this pair VW is an edge. In other words, it's a graph where all pairs of vertices are edges. Okay? Yoklama aldım ama rate yazacağım. Okay, so we denote this complete graph with Kn. We denote this denote a complete graph with n vertices by Kn. So you can draw these pictures, basically. K1 is just a point, but K2 is just like this. K3 is a triangle. K4 is, you can sort of see how it is. And there's no harm drawing these lines here, but you can also draw it like that if you. K4 is planar, like you can draw it actually without any intersections. K5 is not planar, actually. We will start seeing these discussion later. But if you try to draw K5 on the plane with no intersections, you fail. At some point you have to have basically you have some intersections. But K5 is something like that. So what a clique means, a clique is a subgraph which is a complete graph. Okay? So a clique of size n in a graph G is a subgraph with n vertices, which is a complete graph. So, for example, we have a, say, complicated graph which has lots of knots. you can ask yourself, what's the clique size of this? So the clique size of a graph G, there's a different notation for this. You can say alpha G, but we could just say clique size, say denoted by alpha G, is the size of the maximum clique size. So the value, the maximum size of a clique, maximum, and such that G has a clique size n. So you could see a graph like this. You can ask, what is the clique size of it? So in this case, you can see the biggest complete subgraph is a triangle. And if you had this one also, then clique size becomes 4. So in this case, for example, the clique size becomes 4. But if I didn't have that line, it will be only 3. So the clique size is the maximum you can find. Now, the kind of difficult result that I mentioned is this result. A graph with 2m vertices and m squared plus 1 edges necessarily contains a triangle. So a clique of size 3. So in other words, if you have 2m vertices and m squared plus 1 edges, your alpha G is bigger or equal to 3. At least you have a triangle. This is actually optimum. So you can see that if m is 3, in general for every m, you can find graphs which has m squared edges like this, which has no triangles. Actually, you can extend it to m. Let's do. So this is the, for 3 you can just focus on here, but this is true for general m. So make a graph where from every vertex you go to all the vertices on the other line. From here you go all the, like so. You go all of them, basically. And because you go from every vertex to every vertex on the upper level, from here you have m edges, from here you have m edges. So totally m square edges you will get. And 2m vertices, because you have 2 layers. And this graph has no triangles. Like you cannot find a triangle. Because to form a triangle, you have 3 vertices. So out of these 3 vertices, 2 of them will be in the same row. And if they're in the same row, there's no edge between them, by the way we described this graph. So this is an example. So geez, there is a graph with 2m vertices and m square edges, which has no triangles. So you can see that this plus 1 makes the whole difference. If you just have 1 more, suddenly you have to have a triangle. That's optimal. So the plan I have was to start with the proof of this, but let me just mention one result and then we prove this. So before we prove this, that there is this another proposition which says that for a graph G with n vertices, the independence number G is actually bigger or equal to sum of and where di denotes the degree. Say the vertex set is just this vertices. It denotes the degree of the vertex. So you can find like formulas like this. Sum of the degrees gives you a lower bound for the clique size. So you always have something bigger than that. Sorry, it's not sum of the degrees. One or sorry, it's actually reverse relation to the degrees. So when the degree is bigger, the lower bound is small. Degrees are big. This is yeah, this. Okay. Okay, it's double. Okay, this is the formula. So when they are close to n, these are big, these are small, and then this thing is bigger. So when degrees are bigger, you have bigger clique size. So there's a bigger chance that you have a clique, bigger size. So you have a formula like this. For example, if you have a graph, let me give you one example. Suppose you're looking at this graph. It has n equals 7. So it has 7 vertices. And the degrees are, you can calculate degree at each vertex by looking at how many edges are attached to it. So degree at 1 is 3, degree at 2 is 3, degree at 3 is, yeah, you just count these, 5. Degree at 4. 5, degree of 5 is 1, degree of 6 is 2, degree of 7 is 3. So what you get is, maybe I should use a different notation. Let's call this MC, maximum clique size, MC. MC. Okay. Just to remind us that Let's use MC instead of MC. So MC of G will be bigger than the sum of its difference to N. So you'll be looking at 1 over 4 and 1 over 4, 1 over 2, 1 over 2, 1 over 6, 1 over 5, 1 over 4. Okay, so 1 over 2 plus 1, 11, 30, 1 over 4, 3 over 4, 7 over 4 plus 11 over 30, 2, 70, 105 plus 22 over 60, 127 over 60. This is 2 point something, 2 point something. Because it's 2 point something, because this is an integer, maximum clique size should be 3 or bigger. So this gives that the maximum clique size is bigger or equal to 3. And for this shape, I guess this is actually the best, this is the accurate answer. So maximum clique size in this case is exactly 3. There is no 4. So only triangles exist. You can see that you can make it explicit. It's correct, right? Maximum clique size 3. Can you see a clique of size 4? Right. Yeah, if we had this line, I guess, maybe. But so in this case, maximum clique size is 3, and you get exactly the lower bound. Okay. We'll develop on this and make even more explicit things. But do you want to see the proof of this triangle theorem? This is actually a nice result, but it involves some writing. So I can prove this if you want. I will not be proving this, but I can prove the first one, like why this is true. Why is this true? Proofs of these involve some of them more advanced group theory, graph theory, but things like this we can prove. It's not easy, but still it's provable. So let's see how you can prove that you have 2 m vertices and m squared plus 1 edges, that you want to show that there's always a triangle. So here's the argument. Because you have 2m, first m is equal to 1 is the easy case with 2 vertices. And then the number of edges, so number of vertices is 2, number of edges is bigger 1 plus 1. So you have so it's not possible with m equals 1, right? So we should be saying that m is bigger than 2. Okay? Because 2 vertices you cannot make a triangle. Okay? So this doesn't make sense. So let's look at m equals 2. M equals 2 means you have 4 vertices. And how many edges? You have at least 2 squared plus 1, 5 edges. At least this many. Does it look correct? If you have 5 edges, you always have a triangle. So this is actually maybe a starting good point of more general argument. You take two vertices, I and j, where there's a edge between them. Because there's a lot of edges, you can choose one of them. And then you can look at the graph that are attached to either I and j. So if something is attached to I, it is in that graph. Maybe this is this green table. Do you see a simple argument for m equals 2 that I won't use the general argument? If you have more than 5 edges, why do you have a triangle? I mean, it's easy with 5, right? I mean, I only put one edge. You have to put one more edge. By symmetry, I have to attach to one of them. So it can be between them or... Do you see a simple argument for m equals 2? Here's the general argument. Let's see what the general argument is. And then we can try to see if we can make this m equals 2 also fit into this. So the general argument is you have 2m vertices. 2m vertices. So out of them you choose 2 of them, I and j, so that there is an edge. So we assume that there are this many edges. Let ij in the vertex set such that ij is an edge. Okay. Now look at, consider all the vertices. Consider the subgraph of G formed by vertices which are attached to either I or J. So you have this kind of shadowy graph formed by vertices that attach to one of them, sometimes both of them, but this is the graph that we're talking about. So we choose an edge here, and we look at the subgraph of these things that attach to this. So let m be the number of vertices in the subgraph. So we are talking about either attached to I or J, so we exclude these two, right? So we already don't have those two. So then number of vertices here should be 2 less than the old number of vertices. Okay, it could be equal, but it is 2 less. So we are in the 1 less situation. Okay. So number of vertices is 1 less. So there are two cases. Maybe I should say it this way. And n be the number of edges. So v be the number of vertices. I say n be the number. So number of vertices is less than 2 times n minus 1. And there are two cases. So in this graph, we have at least 2 less vertices. So we're talking about at least the situation with m is 1 less. But number of edges could be more. Like number of edges, this n. It could be either m minus 1 squared plus 1. Let me write it. So either bigger than this or less than equal to square plus 1. Okay, so we'll come back to this situation. So you have two cases for number of edges, either too big, like m squared plus 1, or less than m squared. I wonder we can run it for this case. For this case, m is 2. So either it's both of the vertices are involved, or less than them, or more. More than m squared plus 1. M squared is 4. In this case is always the case. So for this one, it will be always too little here. You can only have one edge. 1, 2, 3, 4, 5. So the maximum you get is 5. So this could be it's possible. Okay, so what goes wrong in each case? You can either have a lot of edges in this subgraph with m minus 1 vertices, or you could have very small amount. If you can show that each of these cases gives you a triangle, or you can show that one case gives you a triangle, but other case cannot happen, then you'll be done, right? So this is a typical induction situation where you're looking at a subgraph with less vertices, and if it has a lot of edges, then you get a triangle. What is the condition to get a triangle if I have m minus 1 edges? What is the number I should be to be satisfying? Look at this. If it has m squared plus 1 edges, it already has more edges than you will want. Like this is a less number of vertices, and it has a lot more edges than you will want. Like this was the. So you have less vertices, but more edges than you will want. So this situation, there is definitely a triangle by induction. So let's write this. In case 1, n bigger equal to m squared plus 1 implies that there's a triangle in the subgraph. By induction. So you look at the subgraph, but the subgraph still has a lot of edges, and it has less vertices, but it has still more edges than you will want. Actually, the explicit borderline should be more like m squared minus 2m plus 2 or something. But this is definitely bigger than what you want. So because of that, you're fine. So number of edges are too big. You still will have a triangle. Let's look at the other case. So in case 2, we want to see something going wrong. So we are assuming that now edges in this graph attached to I or j is less than or equal to m squared. So these are the edges that are attached to either I and j. So we have two vertices, I and j, with a line between them, with an edge between them. And we're looking at vertices around it, which are 2 times m minus 1 of them. And then we found out that we have less than m squared edges. Okay. Let's look at it this way. That's basically. Okay, so this n will be the number of edges for the subgraph. On the subgraph, which are not attached, either I or j. So these are the ones which are not attached. So we're looking at n is the outside word. That's why when it's bigger than m squared plus 1, we're done. Okay. So this is, we don't need to evaluate. So if you have the outside of I and j, or the word attached to I and j, if the outside has more vertices than m squared plus 1, then by induction, then you're done. By induction. Because you always have less vertices, and then you still have a lot of edges. So by induction, you're done. Now, if you assume that the outside word has very few edges, this is the case we need to get rid of. Okay, so the outside word, the ones that are not attached to I and j, they have very small number of edges. This is the case we're looking at. Okay. Now, if the edges outside are less than this, now you can estimate the edges which are attached to I or j. Okay, so the edges, the number of edges in this subgraph, so say this is your G prime, in G prime is, let's call this E prime. So what is the number of E prime in there? We already have m squared plus 1 edges. And in the outside, we assume that it's less than m squared. So this should be bigger or equal to this one. Sorry. Now I have to make one more correction. So because I want to put I and j, suppose the beginning graph is m plus 1. So these m's are actually correspond to the vertices not in I and j. Sorry. Now we know this. Okay, sorry. So we start with 2 times m plus 1 vertices. So we are in the m plus 1 situation. We already know this. We exclude I and j. So the remaining is 2m vertices. And then n of them is outside of this circle of involving I and j. And if that n is bigger than m squared plus 1, then we are done by induction, because we're talking about 2m vertices, since we have 2m vertices here. So it is induction statement that gives you. Now for the case 2, I have to start with m plus 1, square plus 1, minus n. Okay. So now I have this many edges already. Take out the n of them, which are outside. And I already have an estimate for n. Says it's smaller than m squared. So this whole thing is bigger than this. Okay. So now it's more or less what I want. So we are in the bigger case, but we take out the smaller case. Now you get 2 times m plus 1. So the number of edges in the subgraph which involves I and j is 2 times m plus 1. Okay, that's what we wanted. Sorry about this. So yeah, you have to start with m plus 1 vertices, where I and j is just those 2 extra vertices. You have to look at the subgraph which involves I and j, and then outside of subgraph. This outside of subgraph has some edges, say that is n. For n, you have 2 cases, either bigger than this or less than this. So for this case, you just follow through induction. Now for this case, we want to get something a triangle out of this case. So this case means you have very few number of edges outside of this area where they involve I and j. And we find out that for that area, which we call the G prime, the number of edges, which is difference, is bigger or equal to 2 times m plus 1. So it's 2m plus 2 basically. So why this gives us a triangle? Do you have any idea why it gives a triangle? So we are talking about these things that involve I or j, and I have 2m plus 2 edges. So how many vertices you have here? Because 2 of them here, what is left is 2m vertices, right? You can have 2m vertices there. So we found that if all 2m vertices are involved, these things are attached to either this or this. Everything is attached to either that or that. But now in that area, I have more than 2m plus 2 edges. What does it mean? I have 2m vertices. They're attached to either I and j. But I should have 2m plus 2 edges from those things to I or j. So that means if Vi is attached to only one thing, or I or j, it means it will have only one edge in this set. Same way, if V2 is attached to only one of them, it will have only one edge. So if all of them attached to only one of them, I or j, I will have at most 2m vertices. So that means 2m edges at most. But I see that I have more than that. So there's this one too, 2m plus 1, but there's still one more, which means one of the vertices should be attached to both I and j. Just the numbers doesn't count. Okay? At least one of these vertices must be attached to both I and j. Otherwise, you don't have enough edges. What does it mean if one of the vertices is attached to both I and j?
Since we know I and j is connected.
Yeah.
It
It gives a triangle, right? So we sort of went through a couple of bumpy steps, but at the end, this is where the result comes from. So when you assume that there are less than m square edges outside, the inside you get to have more edges than you want. So in particular, you have more than 2m plus 2 edges. So one of the vertices must be attached to both I and j. Okay? So let me write this here. If each Vi is attached to either I or j, but not both, then we will have less than or equal to 2m plus 1 edges. Since number of edges is bigger or equal to 2m plus 2, we must have a vertex Vi which is attached to both I and j, which has an edge with both I and j. But I and j is an edge, but since I and j is an edge, we obtain a triangle. Okay. So there's a couple of bumps here. I should be more careful of. Okay, so if there's time. Oh, there's no time. Okay, this is the proof, and you see that it kind of becomes difficult to conclude that you get a clique, you get some clique of certain size by arguing through the edges and vertices. Even to get a triangle, we had to do a lot of difficult arguments. We will state some result which guarantees that it's called Turan's theorem, that there is a clique of size k if you have, again, a lot of edges compared to number of vertices. So there are theorems like this that maybe I will state it and then I will finish with that. So there's a theorem called Turan's theorem. This is a generalization of this triangle argument, but again, we won't be able to prove this. A graph with m times k minus 1 edges, so vertices, and k minus 1 choose 2 m squared plus 1 edges contains a clique of size k. This is true for any m, okay? So let m be a number. So for k equals 3, see for k equals 3, this is 2m vertices and m squared plus 1 edges, exactly that statement, okay? So the k equals 3 case is exactly what we just proved. So that means you can generalize to k by giving some constraints. Actually, we can prove this if we assume those inequalities I just wrote about maximum clique size. So if we assume that inequality, by step we can be able to prove this. So you can show that there's always a clique of size k if you have certain vertex and edge number combination. This is a well-known theorem, Turan's theorem. Okay. Maybe on Friday we'll come back to this, and I will start with the statement of this. I'll show you how you can show this using some of the ideas.